Okay, so this red boxed formula is the result that we've just obtained, and I'd like to discuss it a little bit to give you some intuition on how to think about it. Okay, so the first thing that I want to point out, let's think about how the measure would transform. So if we were changing between a variable x and a variable f of x, this is how the measure would transform. So what you can see is when you transform from df to dx, you multiply by a factor of the mod of df dx. But when you transform from delta of f to delta of x, you divide by a factor of df dx. And in fact, we can make this even more perfect. You see, in this red boxed formula, I don't even have to evaluate things at x is equal to x naught. I can remove that because the delta function is only non-zero when x is equal to x naught. And now it really looks like the integration measure and the delta function transform in exactly opposite ways under changing from f to x. Okay, so under changing from f to x, delta of f is equal to delta at the zero of df dx. So we've divided by df dx, whereas for the measure, we have multiplied by df dx. So they transform in exactly opposite way. Okay, so the delta function transforms like 1 over the measure. Well, the delta function is like 1 over the measure. Now, in fact, this should remind you of something else. Do you remember when we were doing dimensional analysis and thinking about the delta function? So we studied a formula that looked like this. Integral delta of x dx, let's go, I don't know, from -1 to 1. That's not too important, but that was equal to 1. Now, the 1 on this side is dimensionless, so it's length to the naught. dx, well, this was a little length. So this we said was length to the 1. And the only way that we can make this function dimensionally consistent is if the delta function itself has a dimension of length to the -1. So you can see in this formula too, delta of x, the delta function evaluated at x, is behaving like 1 over dx. It's behaving like an inverse length. So once again, this should look a lot like, should look very natural given our formula in the red box. Good. Okay, so now how do we use this? So I want to do an example of how you would really use this rule most of the time in practice. So let's imagine that we start off from 3 variables, x, y, and z, and in these 3 variables, we have an integration measure d3x, and we'll make a change to a new set of integration variables, x primed, y primed, and z primed. Maybe these are related by a rotation. So maybe I rotate x, y, and z to get x prime, y prime, z prime. Maybe it's a more complicated transformation. But one of the things I might like to know is, how is d3x related to d3x primed? And remember, by d3x, all I mean, this is dx, dy, and dz. And for d3x primed, I mean dx prime, dy prime, and dz prime. Well, you know the relationship between the two measures. They're equal up to a factor of the Jacobian. And what is the Jacobian? The Jacobian, you know, is the magnitude of a determinant. And that determinant is the matrix of derivatives of the x's with respect to the x primes. So you know exactly how to calculate that Jacobian. Using our rule in the red box above, we could imagine the delta function delta 3x, which is delta of x, delta of y, delta of z. And we can also think about the delta function delta 3 of x primed, which is delta of x prime, delta of y prime, and delta of z prime. Well, the relation between these two is that delta 3 of x is equal to delta 3 of x prime. And now the measure transforms by multiplying the Jacobian. So in the delta function, we should divide by the Jacobian. So that's what the formula would look like. Very good. So we know how to change coordinates, and we know how to relate the delta function in the original coordinates to the delta function in the new coordinates. And yeah, good. Now, our formula in the red box, we wrote down this formula assuming that f of x only has a single zero. Now, it may have more than one zero. So let's write down the most general formula now. So let's imagine that f of x is equal to 0 at x is equal to x naught I. So let's append an index I there, okay? And in fact, I runs from 1 up to k. So we've made it completely general now. The way that our formula changes is that we should now sum from I is equal to 1 up to k. So we sum over all of the zeros, and now that formula in the red box is completely general. You should know enough to actually convince yourself that that formula in the red box is perfectly correct. So try to do that. Try to prove that for yourself using exactly the same methods by which we proved the simpler version of the formula with just a single zero. Okay, so we've got one more idea left for this chapter, so let me tell you what it is. Well, we know that the position operator is not an observable, but certainly momentum is a good observable. And once we've got the spatial momenta, we can work out the energy. Remember the formula that E squared is equal to, what is it, m squared c to the 4 plus p dot pc squared. So I'll put the c's in for now. So if we know the spatial momenta, we immediately know the energy. So we will want to study states that are labeled by their spatial momenta, labeled by p. These states need to be normalized. We are going to want to normalize the states in a Lorentz invariant way. And the reason why we'll want to do that is we want to make Lorentz invariance manifest. We want to make it very obvious that the theory is Lorentz invariant. So one of the things that we're going to do is work out how to normalize our states in a Lorentz invariant way. And in that way, we know that all inertial observers, so an observer in any Lorentz frame, they're going to normalize their states in the same way. That's a good thing. The other thing that we will want to do is we'll want to perform integration. And again, we want to make sure that all inertial observers are integrating in the same way. So we're going to want to define a Lorentz invariant way of performing integrals, of doing integration. So the two ideas that we're going to develop now is how do we come up with a Lorentz invariant normalization for our states, and how do we integrate in a Lorentz invariant way?